Well, so I begin. Last time I wanted to do something and I didn't finish, so let me finish that. I think which I will need, let it be only once, is the following, that if, let me just remind it, if G is a semi-simple the algebra, and then a representation, rho, some space, everything is fine dimensional. Then we consider two spaces. V super rho is the space of invariants. Elements of V which are analyzed by every element of G. G. Maybe sub rho is so we take all elements of V, all elements of G, apply Xi to V, we get some subset of V, and the span of the subset is V sub rho. Then the fact is that both of them actually are sub-representations of V. This is obvious, that the action of G preserves both. So both are sub-representations, and V is the direct sum. This technical result, which will be needed, still has not a very obvious proof. And in this proof we use again, the first time when we use it, I'm not sure that we will return to it any the Casimir operator. First of all, effect from linear algebra. Suppose we have an arbitrary linear operator in some space. Then you consider two subspaces, W1, W2. W1 is the union of kernels. So this consists of all elements which are annihilated by some power of F, not necessarily by itself. This is the intersection of all images. That is, those elements which are images of F, F squared, F cubed, and so on. The fact is that we direct sum, and this is sort of obvious, because if I take F and in some basis I write it matrix of F in Jordan normal form. So like this. Then there is some domain of zeros. And this is precisely W1. Vectors which are linear combinations of any element here, and hence any linear combination, is annihilated by an appropriate power of F. The power is the size of this block. All the rest is W2. Again, it's clear that when you take any element of V, apply F sufficiently many times, you are in this area. And as soon as you are in this area, you actually, every vector here, its image is again in the space and not zero. So it is obvious that this decomposition is precisely with decomposition to these two spaces. Now I need to erase this, or I can actually split the boards. yes. And back to the representations. So I have, I don't want to write again, I have a representation in the space V. I want to prove the statement which is written. And I do this using the dimension of V. Induction. Well, maybe it is reasonable to say that if the dimension is 0, then I have nothing to prove. Everything is 0. Actually, this is 1 also, but I start with 0. So, I have my V, and just imagine that V is the direct sum of two sub-representations, and both are not 0. Then our induction immediately works, because V super rho will be W1 super rho plus W2 super rho, so this is the composition into the spaces with upper and lower row. It also splits into two pieces according to W1, W2. And for these two spaces, my statement holds because of the induction hypothesis. Dimensions of this are less than. Good. How to make this decomposition? In the future, I will prove that actually every representation of semi-simple algebra, finite dimensions certainly, is direct sum of irreducible subrepresentations, but actually this will be, in proof of that, this will be needed. So I will not use, I'm not going to use it now. I take W1, W2, precisely as here, only using the Casimir operator as C super rho. You remember what it is? Yes, C super rho. So I have the sum of G rho of G lower I, composition with rho of G upper I, sum over I, and Gi forms the basis in the complement to the kernel of rho. Do I need to repeat it? The definition? No. So I take this and then I use this. So W1 is this, and W2 is this. Now look at this. Two sub-representations. Why? Simply because C rho commutes with the operator of representations. So if I take any element of W1 or W2 and apply any rho when XC, I will be back to W1, W2. Two sub-representations, right? So again, and yes, and at the level of so here I have this decomposition of representation in some representations, and the only thing which I really need is that both are not 0. Well, I want to say that one of them is definitely not 0. No, I need first to say, I could say it before I say all this. If rho is 0, then V super rho is V, V sub rho is 0, and hence everything else. So rho is not 0. If rho is 0, I don't have nothing to prove. If rho is not 0, then this can be all. You know that the operator C rho is not nilpotent. I made this observation last time, and the reason was, if you remember, that actually we can compute this trace. And finally, it's not 0 if rho is not 0. The trace is the codimension of a kernel of rho. So this is not nilpotent. If it's not nilpotent, then it is not possible that every element of V is annihilated by some power of it, right? The point is precisely an operator such that its power is 0. So its power is not 0. This means that for some s that W1 is not V. If W1 is V, then it is nilpotent. It's the same thing, right? If it is not V, then W2 is not 0, right? So there remains only one case. What to do? When W2 is not 0. But W1 we don't know. W1 is not 0. What does it mean? This means precisely that C sub rho is invertible. So this is no zero eigenvalues. If so, take, I want now to compute both V super rho and V sub rho. V sub rho. V, take any V. Then V is 0 of some W, where W, because 0 is invertible, right? This is what? This is the sum rho of Gi W. But this thing shows that this is in V sub rho. It is a sum of rho, something applied to something, right? So every V in V belongs to now the next thing. If rho of C V, so let V be V rho. If this means this, right? But this definitely shows that this is 0. This is 0, right? This is C rho, so C rho of V is 0, so V is 0 because C rho is invertible. And this is all. I don't know what else to say. So in this dangerous case, we have that V sub rho is V, V super rho is 0, and I don't see any reasons to doubt that the sum, that the V is direct sum. Now the theorem is done. Questions? Remarks, whatever. If no questions, no remarks, no whatever, I go further. So this is, I am not sure that, no, probably I will mention Casimir operations at some moment. So just let me say that certainly it is an important thing. The small proposition which we proved using it is definitely not all that we need. It is really an important tool in the representation theory. I mean, Casimir operators. Yes. Now I want to introduce and to discuss three things which actually are, again, very common in the theory. The fact is that we will discuss them in a very broad context, much broader than the one which we will use in reality. my next section is called Cartan algebras, weights and roots. I begin with weights, then roots, then Cartan algebras. But everything will be done in sort of two general contexts. A weight. I consider, first of all, a nilpotent Lie algebra over C. Actually, sometimes I will need less than that. Simply, it's sufficient for me to consider this case. So H is nilpotent Lie algebra, and the ground field is an algebraically closed field, like C. I consider representation of it. In some space V. Then a weight. Consider an arbitrary element lambda, an arbitrary form lambda on H. So lambda element of the dual space to H. Then I take in V the following thing: all elements V in V, such that rho C minus lambda of C tenth identity raised to some power applied to V is 0. Also, this is another notation which actually we'll be using. V super lambda. You understand that if we have not a representation but just one operator, then this is a very common thing. We consider an operator in some space V, take a number lambda, and then take those elements in V such that f minus lambda to the power n applied to V is 0. This is the usual part of the space V which is used in the creation of the Jordan normal form, right? Good. Here, however, I want this to hold simultaneously for all elements elements of H with different lambdas. Lambda depends on the element of H, and this is a linear function. So you look at this. There exists another definition which is related to lambda. I called V in V, just one vector. Well, I consider, no, I call lambda a weight if there exists a non-zero vector V in V such that lambda the same property. So rho of Xi. No, lambda. I just require that rho of Xi V is lambda of Xi V. So V is an eigenvector of the operator rho of Xi with the eigenvalue equal to lambda of Xi. This should hold again for every Xi. Then I call lambda a weight and V a weight vector. there is something which probably should be regarded as obvious. Namely, lambda is a weight if such a V exists. And V lambda is not equal to 0 if and only if lambda is a weight. Sort of obvious from the definition in one direction. So if lambda is a weight, we have such a vector V, it definitely belongs to this v lambda, hence V lambda is not 0. If V lambda is not 0, then definitely we can find within this V lambda elements with this property. Because we apply this to the power n until we take a vector V and apply these operators to V. And at some moment I didn't write this. So for n sufficiently big, I didn't write for some n. But some n means n sufficiently big. So if we apply this operator to V, this being square, cube, and so on, then at some moment we get 0. Right before it, we have a vector which is annihilated by this operator. It is an eigenvector. So this is sort of obvious. Then two more things. Well, so far questions. Then two more things. First is that the spaces V lambda are subrepresentations. So I want to say that if V belongs, so first, V lambda is a subrepresentation of my representation. And this means that we have some C in H and some V in V lambda, then rho C. V also belongs to, this is 1. And the second thing is that actually V is the direct sum of all such subrepresentations. So this is also a decomposition of representation in the sum of subrepresentations. Here, H is nilpotent. How would you estimate the reality of these things? I want to say that it is not hard. I will give a proof immediately. But one thing which can actually not be, maybe not visible immediately, that here, when I prove this, it is important to me that H is nilpotent. So far, what I did, who cared about the importance of H? But now it becomes important. So I prove first the statement 1. Actually, I will prove some stronger result. And after it, I will deduce from it the statement 2. Yes, Henry.
So in terms of linear algebra, you're just basically putting it in Jordan, all of them in Jordan form so that the blocks agree?
Yes, actually. Yes. So V lambda is a subspace. Yes, you can say this, that it is known from linear algebra that every operator, there is a basis for which it has Jordan form. But here you have not just one operator. You have many of them. And this basis should be chosen simultaneously. That is the spaces V lambda, but I say more because I say this is subrepresentation. And this is some where I begin. And this actually, the proof of this, as you will see immediately, will require the nilpotency of the Lie algebra. So, you proving this, I prove slightly more, because I fix G and H in H, and then I prove that rho of G applied to V, rho of H, lambda of H, and this is something which doesn't know anything about the representation. V is my space, this is an operator, this is a number, is within V again. This is stronger than just that. So this is for every particular G. Now, how to prove this? Well. We need to prove that something. Induction. Induction. Since the real algebra is nilpotent, H is nilpotent, this means that if we take G and apply as H sufficiently many times, it will be 0. K is some number. And believe it or not, I will use the induction with respect to K. Say if K is 0, then G is 0. Then I don't see any difficulty in this. And now I will prove this using the induction with respect to K. Now, what I do now, I take some vector V in this, and I want to prove that I apply to it rho of G, right? I apply to it rho of G, yes. And I want to prove that again here. So I want to prove that if I combine this with rho of H minus lambda of H to some reasonable power, this will be 0. So this is what I want to prove. Now, certainly it will be more convenient to apply this first. For this purpose, I take this rho of G, and I want to take it through everything. Look. So this is equal to what? Rho of G I do not think I will have any problems with this. Plus, when I take this rho of G through everything, then at every step, it may happen that I will have to take a commutator, right? Of this with this. This, from the point of view of commutator, is nothing. It is a scalar operator. So with this, so what can happen? That here remains rho of H minus lambda of H to some power S applied to V. Then rho of H G, and then the remaining thing. Rho of H minus lambda of H to the power, by the way, n minus s minus 1. Whatever power, it's not very important. S from 0 to what? To n minus 1. Okay? Now look at this. N, suppose that n is very big. Then of these two numbers, this or that, one is also sufficiently big, right? Very interesting. If S is sufficiently big, you remember, I want to prove this is 0. That, I didn't say this certainly is 0 if n is big enough. So we can forget about this. So if S is big, then it is 0. This is 0. Right? If S is not very big, then this will be sufficient, rather big. And now look at this. This thing, whatever you wish, will be still in V rho of H lambda of H, right? If you apply this several times, this still will be annihilated by sufficiently big power of this. And we apply, so we take this element, we can denote it somehow, we apply it to this, not rho of G now, but rho of the commutator. And we want that, again, that this is in that space, right? So we want that this, and then the most interesting observation. You see, if add to the power k hg0, then add h to the power k minus 1 hg is 0. Simply because this is add h applied to g, right? So this commutator, actually, for this commutator, this number k becomes k minus 1, and we have our induction. So we see that this, if S is not, actually S is arbitrary. This belongs to V rho of H lambda of H. And this is annihilated by this if N is sufficiently big. So S is not so big. This is all. For the part 1 of my statement. Okay? So yes, we have a family of representations. Now the second part. The proof of the second part is not this spectacular. We need to prove two things. First, that so we have the spaces V lambda I for some amount of lambda i's, right? Actually, finitely many of them. Roots. We have this. First of all, I want to say that the sum of V is direct. Which means, as you understand from linear algebra, that if we take one element from each of these spaces, and these elements happen to be linearly dependent, all of them are 0. So vectors, randomly chosen vectors, vectors from these spaces cannot be linearly dependent if not of them are 0. You understand my statement? Now I want to say that this is a theorem of linear algebra. Certainly say that it's weight, linear algebra, but forget about it. You have roots, linear forms in some vector space, all are different. And there exists an H in H, such that all lambda I of H are different. You understand? Two such forms are equal to each other in very small space. So we do not consider, we consider just if V is in V lambda I, then in particular it is in this. And these vectors cannot be linearly dependent. This is effect from linear algebra. Vectors from different parts, Jordan parts, let me call it so, of a space V cannot be linearly dependent. So the sum is, then the last part, we want to prove that actually V is exhausted by this. Here I want to say that if V has only one root, then V is V lambda. If lambda is the only one root, then V is V lambda. Only one root. Wait, excuse me, wait. The word root will appear in a second. Only one weight, then V lambda, then V is V lambda. If V has more than one weight, then then it is reducible. And as soon as it is reducible, we can apply the same result to each part. So this is something which is proved without any difficulties. In this proof, this strange observation that if G is annihilated by add H to some power, then the commutator of H and G is annihilated by slightly by a smaller power, which gives an immediate induction, and this sweeps everything. It's all about weight so far. Want to say something? Then roots. Then roots. And here my setting becomes sort of more sophisticated. I have two Lie algebras. G, some Lie algebra, absolutely arbitrary so far, and H, subalgebra which is nilpotent. Then I have the following representation of H. If it is a subalgebra, then of G. Then we can take commutators of elements of H with elements. It is not an ideal, obviously subalgebra. Then I have a representation of H and G, just commuting with elements of H. No comments? Then my previous theory can be applied to this. H is nilpotent. So the space of this representation, which is G, has this, oh, not here, it was here, this weight decomposition. Right? And if a representation then has weights, and this weight decomposition. We have just done it. In this case, weights of these representations are called roots of G with respect to H. So at this moment, such a strange thing, we need to fix two Lie algebras. G, which is I don't know what, and H, which is nilpotent. And then using this, so G becomes a direct sum of spaces G alpha. And at this moment, I want to say that the following holds. Here I certainly need to say that alpha is a root, beta is a root. If alpha plus beta is not a root, then this is simply 0. So if alpha plus beta is not a root, then my statement means only that these two subspaces commute. This proposition is sort of more obvious than it should be. Really, take my notations. G1, G2, G1 and G alpha, G2 and G beta, and take their commutator. And first, I just want, I think that what I want to do requires more room. I just want to take this G1 and G1, G2, and I want to apply to it an element H, right? Yes, add H. H, yes. Minus the lambda is alpha plus beta. Times H, I want to apply this to this. At the moment, I do not raise it to any power. I will raise it later. Very interesting. What will I get? First, this. It will give me, according to the Jacobi identity, H G1 G2 plus G1 H G2. Very interesting. Now this, and I prefer to write this in the following. So I apply alpha plus beta of H. So this is I didn't say that. You understand? Alpha of H plus beta of H. Yes. I apply this to this and subtract, and I prefer to write this as two different terms. So first I take alpha of H G1, G2, and second I take G1 beta of H G2, if you don't mind. Okay? Then I combine this expression of two terms into two parts. I take this, and I take this. And what I get is the following. It is add H minus alpha of H G1. So this is applied to G1 G2 plus G1 Please look at this, and this is my this is what I wanted to do on this board. So a computation, I don't see where you can have any difficulties. But now what happens if I apply this operation just one time? When I apply this operator, I apply either this to this or this to this, right? If I do it many times, I apply them sometimes to one, sometimes to another one. So this is the sum over, I will keep my notation P, and choose P, to the power p g1 Fuchs add h minus beta of h to the power n minus p g2. And now I just want to say, is it okay? I would just want to say that if n is big, then either this is 0 or this is 0. If so, then the whole thing is 0. Which is the end of this proof. Now I have 4 more minutes, just some final remarks. So G alpha, you remember what we proved? We proved that G alpha, G beta, definitely so. This is precisely what we proved. What about G0? G0. I can say that this belongs to G0. So G0 is a subalgebra of G, right? Very interesting. How much this subalgebra is, you certainly can, if you're on the algebraic side, you can add to it that every G alpha is a representation of G0. But I don't want to say this. So what do you think of this G alpha? I think personally that it is not very much 0. Because definitely H0 contains H. H, you know, all the operators are nilpotent. Add H in H is nilpotent. So this is definitely true. Can you expect that here you will have the equality? I can say immediately no. Because if it happens that H, excuse me, is contained in some big and important subalgebra, then G0 also contains K. Because then the operators at H will be nilpotent also on the operators at K are nilpotent on K, in particular operators at H nilpotent. So this is so. I do not say that actually G0 contains anything else. But here comes the definition, and maybe it is not very fair to finish with this definition, that still it is imaginable that G0 is equal to H. If G0 is equal to H, then H is called the Cartan algebra. So it is an nilpotent subalgebra of G with this strange property that G0, defined as before, is H precisely. Then, so in particular, H is not just nilpotent, it is a maximum nilpotent subalgebra, so it is not contained in any bigger nilpotent subalgebra. Then it's called Cartan algebra. My next goal, unfortunately not today, is to look at Cartan subalgebras. And the first thing, do you expect that such subalgebras exist at all? We will see that yes. And I will give a construction of some Cartan subalgebra. No, I cannot even say how it is done. It's written in my notes, but who will take care of my notes? Next time I will explain there are Cartan subalgebras. We'll give you some construction. And we'll say, whether you believe or not, I will not prove it, that actually this construction gives all Cartan subalgebras. We will need Cartan subalgebras in the case when G is semi-simple. In this case, the Cartan subalgebra will be not just nilpotent, it will be commutative. But in general case, it is so. Say if H is nilpotent itself, if G is nilpotent itself, then G is the only Cartan subalgebra of G. And maybe not commutative. Good. So see you next time.